In this episode of Things I Learned About Cloud Spanner, we look at write batching to help a database specialist accelerate their data load. Will we find the right strategies for higher throughputs? Stay tuned to find out. In the previous episode, I helped my friend Anna and her company Pile of Gadgets, an online shop for gadget fans. We were able to solve a hotspotting issue during their data load that kept the throughput low and their Cloud Spanner instance underutilized. By choosing new well-distributed primary keys for their tables, we saw an increase in throughput and utilization. Now we are going to see if we can improve the data load performance even further. Their data load app, which reads records from CSV files and writes them to Cloud Spanner, was writing only one row per transaction. Since our goal is to load data as fast as possible, loading with a single row per transaction doesn't sound like the optimal solution. It seemed obvious to batch as many writes as possible together to see a considerable throughput boost, while staying below transaction limits, of course. The records we were loading are fairly small, so we increased the batch size to 1,000 rows per transaction, and expected much higher throughputs due to the reduced client-server communications and transaction overhead. Surprisingly, we only saw a bit more than doubling of our write throughput, 50,000 rows instead of the previous 20,000 rows per second. Don't get me wrong, more than doubling the throughput is great, but we wanted to see if we can improve this even further. As it turns out, we were still missing a step to get the real benefits of batching. The rows that were batched together have well-distributed primary keys, the ones we introduced in the previous episode to fix the hotspotting issue during data load. That means writing 1,000 of those rows with well-distributed primary keys in a single transaction ends up involving many table splits. As you know, a table is split based on size and load patterns in ranges of rows ordered alphabetically by primary key. The responsibility for these splits is then distributed among the available compute nodes, where each split is controlled by exactly one node. Now, when we write to multiple splits in a single transaction, Cloud Spanner needs to coordinate between all the nodes that are responsible for these splits. For that, it needs to obtain locks and serialize the access for all outstanding transactions writing to any of these splits using the two-phase commit protocol. This means the benefits of having multiple rows in one transaction are reduced by coordination overhead incurred by spanning multiple splits. Armed with this knowledge of the inner workings of Cloud Spanner, we needed a way to reduce the number of splits accessed by each transaction to gain the maximum benefit of batching. We went back to our loader program and modified it to load a large number of rows into cache. We then sorted these rows alphabetically by primary key, the same way the table splits are ordered, and partitioned them by our chosen batch size. From there, we created one transaction for each of the partitions. Some might ask here, didn't we just introduce well-distributed primary keys to avoid hotspotting in the previous episode, and now we are sorting? Right. The trick here is that the ordered partitions are distinct in the primary key ranges they write to, spanning fewer table splits and thus causing less contention during writes. As you can see in the graph, this improved our load performance significantly to about 120,000 rows per second, a 6-fold increase to where we started from. Now, to find the optimal load performance, we have to keep a couple of limitations in mind. Besides optimal size ranges for transactions between 1 to 10 megabytes, there is a strict limitation of 20,000 mutations per transaction. Mutation? What is that? A mutation has a special meaning here, where any modification of a single cell in a table or index accounts for one mutation, except if you delete a range of rows. So, for example, if you have a table with 5 columns, and an index defined on 3 of those columns, including the primary key columns, each insert of a row accounts for 8 mutations. Now, if you don't want to write all these logic into your own data loader, you can use the Cloud Data Flow connector for Cloud Spanner. The connector does the sorting, partitioning, and scaling out writes automatically for you. Check out the sample source code we linked in the description to learn more about it. After all these data load optimizations, my friend's company Pile of Gadgets was now happy with the load performance and started to look into how to optimize their apps for scalability and performance. Unfortunately, we are out of time in this episode. So stay tuned for our next one, where we show how to design our transactions for scalability and performance.